It's hard to run in-the-wild studies with mobile robots. You want to study a real robot platform, out in a real environment, but it feels like the robot you want to use may not be able to work autonomously. You could teleoperate it, but that would take a lot of person power. Might have to be a short study. But what if you could do something in between? Use the robot you want, which may not be able to run completely on its own, but also not have to teleoperate it the whole time. We found ourselves in this situation when we wanted to deploy a Mayfield Kuri in the halls of our building. Kuri is an expressive and engaging robot, and we wanted to have it moving around the space for an extended time. But as an affordable consumer product, it doesn't have the sensors or compute to navigate a large environment autonomously. We realized that, for our purposes, the robot didn't actually need conventional navigation capabilities. It was fine if it didn't know where it was, as long as it traversed the halls. It did have to get back to a charger from time to time, but maybe this could be handled with some help from a human. Maybe our robot could use wandering.
Wandering has been around in robotics since at least the 1980s. One prominent example is the early Roomba, which would cover a room by moving in a line, bumping into an obstacle, and then turning. Yet, wandering robots have not been common in HRI studies, where we often choose full teleoperation, also known as Wizard of Oz, instead. We searched HRI papers from the last 5 years and found that less than 50% of mobile robots deployed in the wild were autonomous. This makes sense when you consider that the mobile robots that we often study in the HRI community prioritize expressivity and interactivity over navigation capabilities. For example, Cosmo cannot navigate a surface larger than a tabletop. Kuri cannot localize in large spaces due to its short LiDAR range, and Pepper needs an add-on LiDAR sensor to do as much. It's not impossible to have a robot that is expressive and good at navigating, but robot designers often face financial and technical constraints that result in these trade-offs. Let's consider the approaches conventionally used to deploy mobile robots. Autonomous navigation can enable long-term deployments, but fewer robots have the specs to do it effectively. Lots of robots can be Wizard of Oz, but this requires constant researcher attention, limiting the length of the deployment. Our approach, which involves wandering motion with periodic human help, enables long-term deployments while requiring little researcher time.
We needed a system for our Kuri that could be deployed for several days with only periodic human intervention, effectively traverse the space it was deployed in, and move at a reasonable speed. The target environment was a 28,000 square foot floor of our academic building, which has about 1,200 feet of navigable hallways. The hallways are wide and long, and sometimes Kuri's LiDAR doesn't reach far enough to sense anything at all. Several walls are made of glass, and some walkways are lined with a chain-link banister, things that are difficult to pick up with LiDAR. A cliff in front of the banister can trap robots. Our first attempt at getting the robot to navigate involved using Kuri's built-in LiDAR-based navigation stack. But because Kuri couldn't detect any surfaces in some hallways, it wasn't able to build a map. We tried supplying a map built by a more powerful robot, but the sparse LiDAR readings also weren't enough to localize with it. We then tried to use vision-based localization techniques. With Kuri's camera's limited field of view and its weak onboard computer, as well as the environment's lack of distinguishing features, we found that the robot had to move unreasonably slowly to stay localized. We considered adding sensors, but the knock to battery life and our desire to develop a system that could be easily used on other Kuris persuaded us to try other options.
Past instantiations of wandering behavior usually involve a robot moving in a line until some event signals it to change direction. So we break down wandering behavior along 2 key dimensions: what event triggers direction reselection, and how a new direction is selected. We experimented with different wandering behaviors within this space to see what worked for our needs. Having a robot move a fixed distance and pick a new direction uniformly at random didn't work well. The robot bounces around and ends up getting stuck in a small part of the hallway. We found that selecting directions that are close to the previous choice and clear of obstacles, a strategy we call informed direction selection, allowed the robot to move through the long hallways in our building. Reselecting directions whenever the robot couldn't proceed any further let the strategy avoid obstacles and prevent the odometry drift caused by sudden rotations. Our final system consists of two modules, the wandering module and the human interaction module. The wandering module selects the direction to move in using informed direction selection and executes that motion using an off-the-shelf local controller. Informed direction selection considers a set of directions the robot can move in and selects the one that collides with the least obstacles, while also being as close as possible to the robot's current direction. The robot monitors its progress in the odometry frame and engages recovery behaviors, like rotating in place or moving backwards, if it detects that it hasn't moved for 30 seconds. Although the wandering module lets the robot traverse the hallways of the building, it cannot enable the robot to return to its charger. That's where the human interaction module comes in. The human interaction module enables the robot to use a chatbot to ping one or more designated helpers when it's low on battery and have them put it on its charger. Although for our deployment this form of help is sufficient for letting the robot navigate on its own, the human help module could be extended for other forms of help the robot might need, like asking whether it's going in the right direction. We deployed this wandering robot system for 4 days in our academic building. It was able to navigate all 1,200 feet of hallways on the floor and ran for 32 hours total without once running out of battery. Each of the 12 times it needed to charge, the system notified the designated helper and they placed the robot on its charger. The robot's recovery behaviors kept it from getting stuck most of the time, but the helper needed to manually rescue it 4 times when it got caught on the cliff near the banister. Overall, the system required around half an hour of the helper's time over the course of its 32-hour deployment. This is a small fraction of the researcher time that a Wizard of Oz deployment would have required.
So, you want to run an in-the-wild mobile robot deployment, but the robot you really want to deploy may not be able to navigate autonomously. Depending on the goals of your deployment, wandering may be worth considering. If you're investigating how humans react to a robot in their environment, how a robot can engage or interact with bystanders, or how a robot should interact with remote users, it may be a good fit. Using wandering can reduce development and setup time, and can enable longer deployments than are generally done with Wizard of Oz. If you're one of the several dozen labs and has a Kuri, you can use our system out of the box. For other robots, the paper has pointers for how you can develop a wandering system. If you're on the fence, the paper also has a deeper exploration of the trade-offs between autonomous Wizard of Oz and wandering approaches. Whether it makes sense to use wandering in your study is something only you can judge. But the next time you're crunched between a platform that can't navigate on its own and a study that would be difficult to run with teleop, we hope you think, maybe I can make this work with wandering.